You're listening to DTFHN for July 18th, 2026. I'm your forensically reassembled host, Jack Hacksmith. We are your daily tech feed for Hacker News, a website where mass curiosity occasionally produces enlightenment. Today's a day for poking old things until they confess new secrets. Let's get into it. I've spent enough time staring at binary file formats to know that the spec is never the whole story. The spec tells you what's legal. The interesting stuff lives in what's technically not illegal. So, this developer, Marisi, looked at Regressive JPEG. You know, the ones that load blurry first and then sharpen. And asked a beautifully deranged question. Each scan in a Regressive JPEG explicitly declares which frequency range it's overwriting. What if you just kept going? What if scan 11 overwrites what scan 3 already rendered? What if scan 20 overwrites scan 11? The answer is you get animation inside a single JPEG file. One file. No JavaScript, no video codec, no container format. Just a JPEG that plays like a flipbook as it downloads. The technical elegance here is worth pulling apart. Regressive JPEGs work by splitting the image into multiple scans. First, the DC coefficients, basically a 16 by 16 pixel thumbnail, then progressively higher frequency detail. Each scan has a header that says exactly which DCT bins it covers and at what precision. The decoder just renders whatever it has so far. Marisi realized that if you concatenate multiple images and strip out the structural markers, the decoder treats the whole thing as one very long Regressive JPEG. Each new frame's DC scan overwrites the previous frame's data. The constraint is beautiful too. Most decoders tap out after about 90 scans. Probably a safety valve against zip bomb-style abuse, so you minimize scans per frame by using DC-only images, which gives you 90 frames of animation in a format designed in 1992. And here's what I love about this. The JPEG standard is completely open. It's an ISO spec. Sure, but the reference implementation is libjpeg, which has been open source since the early 90s. That's why someone can do this 34 years later. Because the format is inspectable, the code is readable, and the behavior is observable. You can open a hex editor and just look at it. Try doing that with a proprietary image format behind an API wall. The comments immediately went where you'd expect. Steganography, trolling, someone pointing out you could build a crude webcam stream by having the server generate the JPEG on the fly and throttle the output. All of which are terrible ideas. All of which are possible because the format is transparent enough to abuse creatively. This is builder culture at its finest. No grant proposal, no product roadmap. Someone saw a gap between what a format was designed to do and what it could be made to do, and they walked right through it. The tools exist. The knowledge is available. The spec is 34 years old, and it's still yielding surprises to anyone curious enough to read it bite by bite. Moving on. In 1960, Mariner 1, NASA's first interplanetary probe, did off course 293 seconds after launch and had to be destroyed. The cause was a single missing overbar in a handwritten mathematical formula, transcribed incorrectly into the guidance software. One symbol, one unit, $18 million in 1962 money, gone in a plume of smoke over the Atlantic. 64 years later, AWS pushed a billing update that confused gigabytes with bytes. The multiplier difference is 10 to the 9th, A $5 monthly bill became $1.7 billion. Someone else woke up to an email saying they owed $437 billion. More than the GDP of most countries. For what amounted to a hobby project. The Mariner-Vine parallel isn't cute, it's precise. Unit errors are among the oldest and most catastrophic failure modes in computing. And they keep happening because the systems that prevent them. Type safety, dimensional analysis, automated unit checking are treated as optional rigor rather than infrastructure. Mars Climate Orbiter in 1999. Pound seconds versus Newton seconds. Same class of bug, same category of preventable. Now run this forward. AWS controls the billing infrastructure for a significant percentage of the Internet's compute. When their billing system hallucinates a 9-order of magnitude error, the immediate human reaction is panic. People in that thread genuinely believe they've been compromised. One person thought the billing alert was a phishing email. Logged into their real account, and the real number was $78 million. That moment of ice in your stomach is not abstract. That's a real person staring at financial ruin before their morning coffee. The comment surfaced something worth sitting with. A former AWS engineer confirmed this is a known failure mode. They meant to charge 5 cents per gigabyte, missed the unit annotation, and the billing system defaulted to bytes. The system doesn't fail safe, it fails catastrophic. And this is the infrastructure we've collectively decided to trust with the operational backbone of modern civilization. The deeper question isn't whether AWS will fix this particular bug. They will. It's that the billing system for the world's largest cloud provider can emit a number 9 orders of magnitude wrong, and the only safety net is a human noticing. It looks insane. There's no automated sanity check that says, hey, this account that's averaged $4 a month for 3 years probably didn't just consume more compute than the entire platform generates. The tools to prevent this exist. Dimensional type systems, statistical anomaly detection, billing circuit breakers. The engineering is straightforward. The incentive to build it has apparently been insufficient. Until the morning your customers wake up owing more than the national debt. Moving on. 49,688. That's the number of unique products in the Instacart dataset, which means there are roughly 1.2 billion possible pairs of items someone could put in a cart together, and 97% of those pairs never appear once across 3.2 million orders. Roger Dickey wanted to find the funniest shopping carts. The combinations that would make a cashier pause, a simple question. But simple questions against large data sets have a way of teaching you something about measurement itself. The first attempt is obvious. Count co-occurrences. Find the rarest pairs. And it fails immediately, because when you have 1.2 billion possible combinations, and 22 million of them appear exactly once, rarest is meaningless. You're drowning in ties. Banana and extra fancy unsalted mixed nuts appeared together once. Organic Hass avocado and baby cucumbers appeared together once. 22 million other pairs also appeared together once. There's no signal, just noise shaped like data. This is where the craft comes in. The fix is a metric called lit. Actual co-occurrence divided by expected co-occurrence. If bananas show up in 30% of orders and milk shows up in 15%, you'd expect them together in about 4.5% of carts just by chance. If they actually appear together less than that, the gap is interesting. You're not asking what's rare. You're asking what's surprisingly rare given how popular each item is individually. And that reframing, that single shift from counting to comparing against expectation, is what turns a failed analysis into results that genuinely make you laugh. Kale and an enema kit, parsley and condoms, adult diapers and baby food. These land because both items are common enough that you'd expect overlap, but the people buying kale are apparently statistically not the people buying enema kits. The whole thing runs on data that Instacart open-sourced years ago for a Kaggle competition. They wanted better recommendation algorithms. Someone used the same data to find the opposite. The anti-recommendations, the combinations no algorithm would ever suggest. That's what happens when you put data where people can reach it. You get uses the original creators never imagined and wouldn't have prioritized. The dataset is still sitting on Kaggle right now. Anyone can download it. Anyone can ask their own weird question. The craft here isn't the punchline. It's the pivot from a metric that doesn't work to one that does. Every interesting analysis has that moment. The point where you realized you're measuring the wrong thing and the right thing was one abstraction away. Moving on. The rational case against the Recurse Center writes itself. 15 years, 3,000 participants. No billion-dollar outcome. By every metric venture capital cares about, this is a failed startup. The founders went through Y Combinator in 2010, pivoted away from their original idea, and landed on running free programming retreats. Free. In New York City, Paul Graham himself called it a crazy plan for a startup. The efficient market hypothesis says this shouldn't exist. Now, consider mycorrhizal networks. Underground fungal systems that connect trees in a forest, shuttling nutrients from where they're abundant to where they're needed. No tree pays for the service. No fungus captures the value. The network persists because the forest is healthier with it than without it. Ecologists spent decades ignoring these networks because they didn't fit the model of individual organisms competing for resources. The networks were invisible precisely because they weren't optimizing for the metric anyone was measuring. The Recurse Center operates the same way. People show up, build projects, contribute to open source, teach each other. The output isn't captured in a revenue number. It's distributed across 3,000 careers, countless open source contributions, massive skills that propagated outward through every company and community. Those alumni touched. The founder, 15 years in, still wakes up excited. That sentence contains more information than most Series B announcements. The comments on this thread are worth noting for what they reveal. Multiple alumni describing the experience as transformative years or decades later. Someone pointing out that the social rules are published openly on the website for anyone to adopt. The pricing is buried in the FAQ because it's zero and they don't want to lead with it. These are design choices that only make sense if you've internalized that the value isn't in the transaction. What actually failed here was the original idea, the one designed to be a business. OkCupid for jobs. The thing that survived and thrived for 15 years was the thing they built for themselves. A self-directed retreat where programmers help each other get better. The market didn't validate it. 3,000 people did. The distinction matters more than most founders will ever admit. So what happens when you take that same builder instinct and point it at hardware? Turns out, porting nanochat to a TPU answers that beautifully. A chat model walks from one framework to another, and the first thing that breaks isn't the architecture. It's a single default value. PyTorch initializes linear layer biases to uniform random. Jax's Flax initializes them to 0. Same math, same shapes, same intent. Different starting conditions. And if you don't catch it, your model trains, converges, and produces subtly worse results. And you'll spend days blaming your learning rate. This is nanochat JAX, a port of Andre Carpethy's nanochat from PyTorch to JAX, targeting Google's TPUS. The technical substance here is worth pulling apart. Porting a transformer between frameworks is not a translation problem. It's a first principles problem. You can't just swap function names. You have to understand what each framework is actually doing under the hood. How it manages state, how it handles random number generation, how it distributes computation across devices. JPEGs doesn't have implicit state. There's no modeled bars parameters you can call to collect everything that needs gradients, every piece of state. Waits, optimizer moments, RNG keys. Has to be explicitly threaded through your computation. PyTorch developers take mutable state for granted, the way fish take water for granted. Remove it, and suddenly you're rethinking how your entire training loop works. The TPU side introduces its own constraints. TPU pods want you to think in terms of data parallelism from the start. JAX's baxes and sharding annotations make this explicit in a way that PyTorch's data parallel historically papered over. You declare how tensors are partitioned across devices, and the compiler figures out the communication. It's more work up front. It's also more honest about what the hardware is actually doing. Now, the meta story. The community flagged this write-up as AI generated, and reading it, they're almost certainly right. The prose has that frictionless, slightly over-explained quality. And this is where it gets genuinely interesting as a cultural moment. Someone did real engineering work. A non-trivial port that requires deep understanding of two frameworks and custom hardware. Then used an AI to write it up. The work is real. The documentation is synthetic. One commenter found it embarrassing. Another found the technical insights valuable regardless of authorship. The tools exist. People are using them. The question isn't whether AI-generated documentation is legitimate. It's whether the code runs, and the code runs on TPUS. Someone just brought a 15-year-old netbook back from the dead with Arch Linux. Pause, and this is the kind of thing that matters. What happens to a computer when you stop agreeing that it's obsolete? This is a question with a longer history than most people realize. In 1991, Linus Torvalds posted his famous Just a Hobby message about a free operating system kernel. And he was running it on a 386, a chip that Intel had already moved past. The entire Linux project began as an act of refusing to accept that existing hardware had nothing left to give. 35 years later, someone pulls an OSI PC 1000HE out of storage. Intel Atom N280, 1 GB of DDR2 RAM. A machine that was already a compromise when it shipped in 2009. Netbooks were defined by what they couldn't do. By 2012, it was unusable for routine tasks. By 2023, it's a museum piece running Windows XP with a cursor that stutters just opening File Explorer. The rational move is recycling. The interesting move is Arch Linux. Arch is the distribution that ships you nothing. No desktop environment, no package opinions, no assumptions about your hardware. You build exactly what the machine can sustain and nothing more. For a netbook with 56 kilobytes of L1 cache. Not megabytes, kilobytes. That philosophy isn't minimalism for aesthetics. It's the difference between a functioning computer and a paperweight. The installation itself becomes a systems education. Verifying disk images with GPG. Burning boot media. Navigating BIOS settings on decade-old firmware. The Arch Wiki. One of the great collaborative documents on the internet, maintained by thousands of volunteers. Walks you through every step. And because official Arch dropped 32-bit support in 2017, this runs on Arch Linux 32, a community fork that exists for exactly this reason. Someone, somewhere, decided that i686 machines still deserve a maintained operating system. No company made that decision. No product manager approved that roadmap. The comments tell a familiar story. People remembering their own netbooks. Someone running Kubuntu on a 2011 Samsung. Impossibly slow, Wayland rendering colors wrong. Another person noting these machines were painfully slow even when new. All true, and all beside the point. The point is that open systems let you decide when your hardware dies. Proprietary software made this netbook obsolete in 2012. Community-maintained Linux brought it back in 2023. The hardware didn't change. The relationship to it did. So what happens when you point that same spirit of discovery outward? Pause way outward. Story 7, First Breath of Another World. One commenter put it perfectly. 48 light years is in our backyard, close enough that we could develop a probe to get there in the next few centuries. And that casual optimism, that breezy few centuries, tells you everything about where we are in this story. The planet is LHS 1140b, rocky. Habitable zone. And now, for the first time, confirmed atmosphere on an Earth-like world orbiting in that sweet spot where water could exist as liquid. The researchers, publishing in Science, are careful. They have not found life, but they've found the precondition for it, which is the kind of result that rearranges your sense of what's ordinary. Here's the question nobody in the comments wants to sit with. If we can detect atmospheres on rocky planets 48 light years away, and we can right now today with James Webb, what happens when we find biomarkers? Not in a few centuries, in a few years. The spectroscopic signatures of life are within reach of instruments that already exist. We are not waiting for some theoretical breakthrough. We are waiting for telescope time. And yet the conversation keeps drifting to propulsion systems and solar lens telescopes and probes that won't launch until long after everyone reading the thread is dead. The displacement is almost poetic. We might be years away from the most consequential detection in human history, and the community would rather talk about engineering problems on a timeline of centuries. One commenter raised the Fermi paradox. The short time window factor. Life on Earth evolved for billions of years before producing a species capable of detecting signals. That window might be vanishingly small, which makes every confirmed atmosphere on a habitable zone rocky planet a data point in the most important statistical sample we'll ever collect. The beautiful thing is that this science is being done with an open instrument. Webb's data becomes public. The methods are published. The findings are reproducible. Anyone with the expertise can pull the spectra and check the work. That's how you do science that matters. You put the tools where others can reach them. 48 light years. Close enough to characterize. Close enough to study. Maybe close enough to answer the question we've been asking since we first looked up. From securing the integrity of scientific discovery to securing the integrity of the software that builds everything else. Every piece of software you run arrived through a chain of hands. Source code was written, dependencies were pulled, tests were run, binaries were compiled, packages were signed. At any point in that chain, something could be swapped, injected, or silently altered. The SolarWinds attack proved this isn't theoretical. Compromised build infrastructure pushed malicious updates to 18,000 organizations through a supply chain nobody was verifying end to end. The fundamental problem is attestation. You can sign a final package. Sure, Debian signs its packages. Most Linux distributions do, but a signature on the output tells you nothing about the process that produced it. Was the source code the same source code the maintainer intended? Did the build step actually run the tests? Did someone insert an extra step between compilation and packaging? A signature at the end is a lock on the front door of a house with no walls. In-toto attacks this differently. It's a framework. Open source, developed at NYU, now a cloud-native computing foundation graduated project. That creates cryptographic attestations for every step in a supply chain. The project owner defines a layout. Here are the steps. Here's who is authorized to perform each one. Here's the order. Every functionary in the chain produces a signed piece of metadata called a link, recording what went in and what came out of their step. At verification time, the entire chain is checked. Every step was performed by an authorized party. Every output of step N matches the input of step N plus 1. The layout itself is signed by the project owner. This is the kind of infrastructure that doesn't make headlines but changes the ground truth. It's been integrated into Debian's reproducible builds pipeline. It's part of the SLSA framework. Kubernetes uses it. The technology exists to make software supply chains transparent and VSI-able from first commit to installed binary. And the architecture matters here. In-toto is not a proprietary service you subscribe to. It's a specification in a set of open libraries. Anyone can implement it. Anyone can verify against it. Anyone can audit it. The security of your software supply chain shouldn't depend on trusting a vendor. It should depend on cryptographic proof that every hand in the chain did exactly what it was supposed to do and nothing else. The tools are here. The specification is public. The question is whether the industry treats supply chain integrity as a real engineering problem or keeps pretending signatures on final artifacts are enough. So what happens when the supply chain itself is fine, but the device on the other end just broadcasts your home coordinates to anyone who asks? I've spent enough time staring at packet captures to know that the scariest vulnerabilities aren't the clever ones. They're the ones that are boring. The ones where you look at the traffic and think, surely not. Surely they didn't just broadcast that in clear text over UDP with no authentication. And then you check again, and yeah, they did. Christopher Childers found that TP-Link's Casa Spot cameras, the ECCOLA, millions of units were responding to unauthenticated UDP queries with the device's precise GPS coordinates. No credentials required. No handshake. You send a packet. The camera tells you exactly where it is on planet Earth. And this wasn't a novel discovery. The underlying protocol vulnerability was documented publicly in July 2016, 10 years ago. TP-Link even patched it in their smart plug line back in 2020. But the cameras kept broadcasting. Let me play devil's advocate for a moment. You could argue the GPS coordinates are only accessible on the local network, so an attacker would already need to be nearby. That's the kind of reasoning that sounds defensible in a meeting and falls apart in practice. Network scanning tools don't respect your assumptions about proximity. And Childress documented something worse. A secondary market attack path. Buy a used camera, one that's been factory reset, and you can recover the previous owner's credentials and GPS coordinates from the flash chip. The reset doesn't actually erase the data. It just stops showing it to you. The engineering failures here are layered and worth understanding. A single RSA private key shared across the entire device fleet. Credentials stored as unsalted MD5 hashes. And when Childress reported all of this through coordinated disclosure in January, the vendor's triage team responded to the GPS finding by referencing an MD5 hash field that doesn't exist in the actual device payload. They hadn't read the report. He had to submit a video proof of concept to demonstrate that their own triage was wrong. This is what closed firmware gets you, not malice. Neglect. When the code is proprietary, there's no external pressure to audit, No community catching the obvious. No mechanism for 1,000 eyes to notice that your camera is whispering its location to anyone who asks. Childress had to physically desolder a flash chip and read it with a CH341A programmer just to see what the firmware was doing. That's not security research. That's archaeology. The patch finally shipped in version 2.4.1 after 6 months of back and forth. The vulnerability had been exploitable for 6 years. The protocol flaw it was based on had been public for 10. And the kicker, the beta patch they pushed during disclosure bricked his test device. He had to do hardware-level recovery to continue testing their fix. The tools to build security exist. Mutual TLS per device key provisioning, authenticated discovery protocols. None of this is exotic. The gap isn't capability. It's incentive. And when the firmware is a black box, the incentive to fix what nobody can see is exactly what you'd expect. Moving on. In 1976, a small company called Zellog shipped a processor that would outlive every corporate strategy built around it. The Zevon turned 50 this month. The origin story matters. Federico Fagan left Intel, founded the Zellog, and designed a chip that was binary compatible with Intel's 8080. Let that architecture decision do the talking. One engineer walks out the door, and within a few years, his new chip runs every piece of software written for his old employer's product. But better, more registers, a single 5-volt supply instead of 3, built-in memory refresh. The Z80 didn't just compete with the 8080, it made the 8080 obsolete while running its entire software library. And because CP/M ran on it, and Microsoft Basic ran on it, the Z80 became the substrate for an entire generation of computing. Sinclair, Amstrad, MSX, TRS-80, the original Game Boy, industrial controllers that are still humming in factories right now, 50 years later. Zellog only stopped manufacturing the original chip 2 years ago. The comments on this one are worth lingering on. People building Z80 computers from catalog parts, etching their own PCBs, learning that writing a compiler is something you can actually do. One person's teacher had a wire-wrapped computer in a Tupperware box running WordStar off a borrowed IBM terminal to write a thesis. That's what an open architecture produces, not a product cycle, a culture. Thousands of people who learned to build because the documentation was available and the parts were commodity. The Z80 didn't just process instructions. It processed engineers. This has been your daily tech feed for Hacker News for July 18th, 2026. This podcast is entirely AI generated. Scripts by Claude Sonnet 4.7. Voiced by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that surprises you. We'll see you back here tomorrow.